Okay, so the first talk today is going to be on Raman Spectroscopy of 3D printed polymers by Vanessa.
All right, hello everyone. We're going to start this day off, on a good note, hopefully. So my name is Vanessa Espinoza. I worked at the National Institute of Standards and Technology this summer. I worked in the physical measurement laboratory with Aaron and Angela as my mentors. And this was in collaboration with the material measurement laboratory, and I worked with the polymer group there. And my project was Ramen Spectroscopy of 3D printed polymers. So a little bit about myself. I go to Texas Lutheran University in Seguin, Texas, so born and raised Texan. I am a rising senior, double majoring in chemistry and physics, and this is my third summer research experience. And this is me working at NIST. So just a little background on 3D printing. 3D printing is an additive manufacturing process by which a digital design is used to build up a component by depositing material. So this is a nice little quick video. So with 3D printing, you can vary different parameters. You can vary the materials that you use for the 3D printers. You can use, but I focus on polymers. You can vary printer types, but I looked at fuse deposition modeling. So with this, it's a layer upon layer building, and you use different, like I said, materials. And so I use, with FDM, you can vary shear rates and temperatures. So with 3D printing, it was originally used for rapid prototyping, but has quickly made a transition into industry and manufacturing. So with this, applications are endless. It's very cost-friendly and cost-efficient. So because of this transition, there's a need to fundamentally understand the physics that goes on with the printing process. And so this is where Raman Spectroscopy comes in. So Raman Spectroscopy was discovered in 1928 by Stevie Raman over here. I worked with a Renishaw, which is just a type of Raman spectrometer. And this is a form of vibrational spectroscopy. And the way that it works is that an incident laser will hit the sample and activate vibrational modes. And so with this, you get two kinds of scattering. You get elastic scattering, which is a scattering that matches the incident frequency, and then you get inelastic scattering, or what is commonly known as Raman scattering. And with this, there is a shift in energy. So we have Stokes and anti-Stokes, which are two different types of Raman scattering. I will be focusing on Stokes scattering. So this is just an idea of how the Raman spectrum will look. So I will look at the more redshifted component. Another subset to Raman spectroscopy is polarized Raman spectroscopy. So I have my nice little animations here. So like I said, different vibrational modes will be activated once the molecule is excited. And these are different types of CH vibrational modes that can occur. So with this, I will look at different orientations of the incident light and see how this affects the alignment of different molecules. So I looked at two polymers this summer. The first polymer I looked at was acrylonitrile butadiene styrene, or what I will now refer to as ABS because it's a lot shorter. ABS is in Legos and computer keyboards and a bunch of other materials, and this is a very useful plastic to work with. So my technical project on this will be to determine qualitative homogeneity of components using Raman, and then to compare my experimental results to previously published work. So just a little terminology. The way 3D printing works, as I said earlier, is it builds layer upon layer. So with this in mind, we printed a sample and then looked at this with Raman spectroscopy. We looked at two different views. So we looked at a side view. So we take the sample that's printed and lay it on its side and look at, do different line maps of that area. And then we also look at the cross-sectional area. So we take that sample, cut one side down so that it's flat, and we can look at it, and it's very nice with topography and things like that. And this is an example of how it will look laying down on the stage. So, what does a Raman spectrum look like, you may ask? This is a Raman shift versus an arbitrary intensity. And so these are peaks that were of interest with my ABS sample. So we did multiple scans of a line map. So like I said in the terminology, we did line maps of different areas. We then did curve fitting of the peaks of interest. So it was a Voigt curve, which is a mix of Gaussian and Lorentzian, I learned this summer. And we looked at these peaks in particular. So this is a acrylonitrile peak, which is the A, butadiene, which is the B, and styrene, which is the S. And these peaks were also peaks that were looked at in the previously published work. So with this, I did relative ratios of area under the curves and intensity of the curves to compare this and see how homogeneity looked within these samples. So this is a nice little, so like I said, I did mini scans, and with this, I was able to develop an average of the relative ratios, and these are error bars. So with my scans, like I said earlier, I went and looked down these roads. In previously published work, they looked through the roads in some sense. And so as you can see based on my graph here, that all these, we were able to determine that all these samples were homogeneous based on many, many data points and many, many hours on the Renishaw. So this is different than previously published work. In previously published work, they said that there was approximately a 30% decrease in the ratio through this interfacial region, so where these overlapping was occurring of the printing process. Reasons that we may have seen differences could have been because of the way that they did their mapping. So when you go through a road like this and go from a peak to a different view of focus and back to that peak, you can run into topography issues, which is something that can easily happen and can then affect results. And I also looked at the cross-sectional area, and they all fell within each other, so this was great for us to see. After finishing with ABS, I then moved on to looking at bisphenol A polycarbonate, or what I will now refer to as PC. This is a very sturdy plastic that we use. It's found in safety glasses, which we all need as scientists. And so my technical project with this was to use polarized Raman Spectroscopy to analyze the alignment of the polymer chains under different conditions. And now I'm just showing you a zoomed out version of a polycarbonate Raman spectrum. And so this is an idea of what it will look like. So when doing this, I will go back to the idea of polarized Raman spectroscopy. I looked at different combinations. So cross and parallel refers to the way that the incident light is changing. And so this is a graph or a spectra looking at the different cross and parallel polarized Raman. And so with this, to start it off, we normalized the graphs to a phenol ring so that we could better compare the different results. The reason that we normalized to a phenol ring was because it's in the backbone and it's not expected to be affected by the parallel polarized Raman. So it shouldn't change in theory. And we were reassured that it did not change when another peak that is associated with the phenol ring auto-normalized. So this is great news. We then looked at differences in the spectra. So as you can see, there are very substantial intensity differences when looking at cross versus parallel. So this was just adding to the story that parallel polarized Raman can help in understanding the molecular alignment of this polymer. So in addition to looking at the change in incident light, we also looked at the change in the sample orientation. So we did the sample aligned across the X and the Y axis. So when doing so, the spectra did look similar at first glance, but after doing a difference in subtraction, X minus Y, we were able to see that there were still differences in the CH stretching region. So this was very good news because it, once again, adds to this whole story of can polarized Raman spectroscopy help in understanding the molecular alignment of this polymer chain? And the answer is yes. So with all this in mind, I come to my conclusions. So in conclusion, based on multiple scans that were done of ABS sample, we were able to determine there was homogeneity within the ABS sample. In addition to this, with polarized Raman spectroscopy, it shows to be useful in understanding polymer chain alignment. However, because I did too many projects this summer, of course they can't always be complete. So there is more work. For further experimentation, we plan to move on to further exploring polycarbonate a little bit more, understand it better with Raman spectroscopy. And then after doing that, we will begin to understand crystallization in semi-crystalline materials. So these, with PCl and PLA, these are other materials that are used in 3D printing. So we're going to just continue with the 3D printing work. I would like to thank AIP, SPS, Angie Highwalker and my awesome group who's here to support me today. This is our group dinner, our group lunch, and there's Adam. He wasn't there that day. Family and friends, and my fellow interns for sticking it out through me. It was a really great summer, and I'm really thankful for this. Questions?
So I was trying to understand the second thing about the polycrystalline things, the glasses that you look through. Was that about 3D printers, or is this something else?
Okay.
3D printer materials?
Yes, so both of these samples, I should have clarified that. Both of these samples are used in 3D printing. So ABS and polycarbonate are both sturdier plastics. So PLA is what most people will use for 3D printing just for fun. ABS and polycarbonate are more manufacturing type plastics, so they are more readily used in industry.
So you weren't crafting a pair of glasses with your 3D printer?
No. I just wanted to give examples of.
Examples that
Yeah.
you test their properties?
Yes.
Thank you.
Any other?
Other questions?
What was the hardest thing about this experiment? What drove you crazy?
So Polarized Ramen, I worked with the lasers, that was awesome. I haven't had optics, and so I feel like that would have helped with originally understanding, working with lasers, doing Ramen Spectroscopy. The Polarized Ramen probably took me a solid week to just wrap my head around. I was like, why is it not changing? Like, I don't get it. Come to find out, halfway plates and me just don't always get along. So that was probably the hardest part, but it was really awesome.
Well, I have a question.
Okay.
Why was ramen used to try to understand what was going on with the 3D printing?
With, like, as a whole?
Yeah, like why ramen?
So, when looking at the different, because with the vibrational spectroscopy, it activates these different vibration modes. For polycarbonate specifically, with doing the parallel polarized Raman, we were able to see which modes were more prominent depending on the orientation of the incident, or the orientation of the incident light. So that was supposed to help us kind of decipher how this molecular chain was, like how it was aligned, how PC was aligned. So that's why it was helpful with that. For the ABS project, it was inspired by previous work. So we kind of used, or I used their original like idea to test it. I wanted to see how my results would compare with theirs. And it was really interesting to see that it was different, but I think that the motivation was from that paper.
And as a follow-up, why was it important to know what was going on with the polymers inside the 3D printed materials?
Okay, so because the transition is occurring, so like it's now being used more in industry and manufacturing, things like that, we need to understand how the molecules are aligned, how their composition is, because in some grand scheme of things, when you vary different parameters like temperature or shear rates, this can in some ways affect the strengths of these materials. So if we use these little spectroscopy forms to understand different components of it, we can then get to the big picture where it's like, okay, does this temperature help this polymer be stronger or weaker? Like, does the alignment affect its strength or weakness, which is really important for industry purposes. Yes.
So this is completely out of my area, but I'm curious if in a long-term goal, if this is going to be used to develop any kind of standards for manufacturing.
I think that it could be very beneficial in that. So when you look at big pictures, there's a lot of different components that add to the big picture, the final product. So I think that Raman Spectroscopy could be very important in understanding one piece of this big project. So I think yes.
Any other questions? We have time for a quick one.
Yes.
Can you watch the slide where you're showing how they sort of sampled across the ABS
Oh,
piece?
like my terminology slide?
Yeah.
Okay, yeah, sure. One
Sorry.
second, I have a lot of,
Oh, no, wait, it was, yeah, either, I think it was like two.
this
Yeah,
one?
where you're scanning, so you guys didn't do like a scan across that, like along that fusion boundary where the...
So we did, I did do that, and it still fell within the lines, but like I said
Oh.
before, there's a topography issue. So I didn't show it because it wasn't the most prettiest data, but it still fell in these lines of homogeneity. When going through this sample, when going through, so I actually did look at here also, and on the cross-sectional area, so the cross-sectional area is the top view. So I actually looked at that weld zone from the top view also, and these all fell within that. With Raman, going in that like in between, we use like a long working objective and things like that. So there's issues with focus, just because it's kind of in between. You're looking in that like middle. It's kind of like trying to get in between the cracks of like your couch. It's not the easiest thing. So we did look at that area and still see that.
Thanks.
Okay. So round of applause, please, for the speaker.